our topic of discussion today now is, we are now getting into the mainstream of communication theory, and the first thing that we like to understand is some basics about analog signal transmission, right? And to keep this discussion simple, we will use a baseband model. We look at the baseband signal propagation or transmission through a communication channel. Now suppose we look at the block diagram of a baseband communication signal transmission system. As we know, we must have a transmitter, and the transmitter has this block has everything in it that is required. The input to this is the message signal m of t. I'll denote the message signal most of the time by the notation m of t. Output of the transmitter is a waveform or a signal x of t, which typically in the baseband context would be a suitably scaled version of m of t, right? Appropriately amplified so as to drive the communication channel nicely. The channel here in general can be modeled by two parts: a part which embodies the effect of distortion that it might introduce, right? And that part can be modeled conveniently as some kind of a filter, some kind of a linear filter. What do I mean by that? It can modify the amplitude of the various frequency components, or it can modify the phase of the various frequency components, right? All these effects can be nicely modeled if you think of the channel as a filter of some kind. So a very simple and convenient model for a channel, communication channel, and that's true for every kind of communication channel, is to think of this as a filter with some transfer function h sub cf. Right? So this models the channel. The second part of the channel model will consider the effects like noise. We know that noise gets transmitted, noise gets added to the signal at various points in the communication system, starting from the transmitter going right up to the receiver, right? All these effects again will be plugged into the channel, and therefore the channel will have a second part which is denoted like this, right? So this here, this block here is essentially an adder which adds to the output of the channel some noise of an appropriate kind which is suitable for use, and that's what you receive at the receiver, right? So the received signal, suppose we were to call it y of t, right, contains effect of transmission through this channel, this filtering that is effected by the channel of some kind, and some addition of some noise, and the receiver is supposed to work on this input y of t to produce. So this is your receiver, to produce a replica of your transmitted message waveform m of t, together with a small amount of noise which it cannot eliminate. So there is an input noise n of t, and the receiver will try to eliminate as much of this noise as possible, and also but there may be some residual noise still left which you are denoting by n sub ot. The receiver has to process the incoming waveform y of t so as to remove the distortion that might have been affected by the channel, might have been introduced by the channel, and also to eliminate as much noise as possible, right? That is the job of the receiver, main job of the receiver. Okay. Now, so this is the model, this is the framework in which we'll carry out the discussion for today, most of today's class. Now our first, you see, we have been talking about channel introducing two kinds of things. One is this effect, the other is this effect. This essentially carries out what we say distortion of the signal. This is additive noise, right? This adds on to the signal. So first let's concentrate, in fact in today's class let's first discuss only about the distortion part, right? What we like to ideally have is what we call distortion-less transmission. And in this discussion we will ignore the presence of noise, right? Let's assume that noise is not there at all. So we'll assume nt is equal to 0, because we want to concentrate on what kinds of distortions the channel can introduce and understand their nature and see whether we can do something about it at the receiver, right? Just to simplify the discussion. Now in this case your received signal y of t, which is basically the transmitted signal xt convolved with the filter impulse response HCT, the filter which models the channel, is what you will get as yt, right? Now suppose you forget about the channel for a minute. Suppose you would like this signal here or at the input to the receiver to be a replica of the transmitted signal without distortion, right? That's the ideal thing that you would like to have. Y of t should be a replica of x of t without distortion. So how can we express this relationship in the most general form? What kind of effects we can tolerate and what kind of effects we cannot tolerate? We can tolerate a scaling effect. If the signal gets attenuated, it doesn't matter, that is not distortion, right? If it simply gets attenuated, because I can compensate for attenuation very simply by suitable amplification, right? The other thing that I can tolerate is some delay, that propagation delay. After all, the signal has to physically propagate from one point to another point, and no matter what is the form in which it propagates, it will take a finite amount of time to do so, and therefore there will be some delay. So as long as the received signal differs from the transmitted signal only in terms of a scaling factor and a constant delay, that's acceptable to me as a received signal, as a replica of the transmitted signal. Do you agree with that? So ideally speaking, by distortionless transmission we mean that the received signal y of t is some constant k times xt, which is delayed by some amount t sub 0, right? So this is a condition for distortionless transmission. If this happens, if your channel only introduces a scaling factor and a delay, it's an ideal channel. Nothing could be better, right? Then channel is a very friendly channel, and that's the kind of channel I'm looking for physically, right? Now let's look at this effect in the frequency domain. What are we saying therefore? What are the characteristics of the channel for a distortionless transmission? Look at what is if you were to express the same relationship in frequency domain, this would be y of f equal to k times e to the power minus j2 pi f t naught into x of f, right? So what are we saying about the transfer function HCF? It is equal to k times e to the power minus j2 pi f t naught. So the ideal channel H sub CF has a transfer function given by constant k into e to the power minus j2 pi f t naught, right? If you were to characterize this ideal channel in terms of frequency domain plots, then what is the magnitude characteristic we are expecting from this? A constant k for all values of the frequency f, for all frequencies f, right? And what are we expecting from it in terms of phase characteristics? Anyone? What will be the angle of HCF? What kind of characteristics we are expecting as a function of frequency? The exponent here, which is minus j2 pi f t naught, as a function of frequency. What kind of? It's a straight line, right, with a negative slope, right? The angle is 0 at 0. It's positive for positive frequency, negative for positive frequencies, and positive for negative frequencies, right? And the slope will be equal to minus 2 pi t naught, where t naught is a relay that's the slope of the straight line, right? So basically what are we saying? That for signal to be transmitted without distortion, the ideal channel would have a flat magnitude transfer characteristics, magnitude transfer function, and a phase function which is linearly dependent on the frequency, right? So that every frequency component present in the signal undergoes the same amount of delay. Basically what we are saying is every frequency component goes through the same amount of delay, and for same amount of delay the phase shift is a linear function of the frequency, right, required phase shift, right? So that's the ideal characteristic. Of course this kind of an ideal channel is too much to expect to be available in practice, right? It's not even required if you really look upon it, because in real terms you will be transmitting a signal of some finite bandwidth, not of infinite bandwidth, right? So in that case our concept of an ideal channel can be made less stringent. In as much as these characteristics hold within the bandwidth of the signal, we should be quite happy, because what happens outside is of no interest, is of academic interest, because the signal does not have any frequency components beyond those values, beyond some value, right? So therefore we can make these conditions less stringent by saying that these conditions should hold within the message bandwidth, right? So let us say if the message bandwidth is b, right, we would like that the transfer function magnitude is constant, equal to k, with between minus p2 plus p. Whether it is constant beyond that is not of any interest to us, right? It may or may not be, because the signal does not have any frequency components there, so it won't bother us. Similarly, these linear characteristics should hold between minus p2 plus p. After that, if it becomes slightly nonlinear or something else happens to it, it's not a straight line after this, it doesn't bother us very much, because the signal does not have any components in that frequency. Is that clear? So an ideal channel in a practical situation would be one which has these kinds of characteristics within the message bandwidth at least. Is that okay? Good. Any questions? So we call here, we could then say that the ideal channel transfer function, instead of qualifying unconditionally this being equal to minus j2 pi f t0, we will say that this should be so for mod of f less than b. That's our condition for distortionless transmission, right? Here t sub 0 denotes the propagation delay, and b here is the message bandwidth, and k is the attenuation constant, right? Now this is what the ideal channel is supposed to do. Real channels unfortunately do not in practice even meet these less stringent conditions, right. Even within the bandwidth of interest, the magnitude transfer function is not necessarily a constant value, there are variations, and the phase characteristics are not necessarily linear functions of frequency, right. So when that happens, the received signal would or would not be a replica of x of t. It would not be a replica of x of t, because it will now go through a convolution of x of t with the impulse response h of t. For the ideal case, what is the impulse response like? The impulse response is an impulse function, right. That is why whatever signal you transmit, it gets in the same form to the other receiver, right. Okay, but in this case it will not be so if these conditions are not satisfied. So what kind of distortions can be introduced? So let's discuss types of distortion. Incidentally, these kinds of distortion that I'm discussing here, we also refer to them as linear distortion, right. Linear because they are arising from the non-ideal characteristics of a linear filter, right, which is being used to model the channel, right. The ideal characteristics are, it should be a linear filter, but besides linearity you want the magnitude transfer function should be constant. A linear filter may also have magnitude transfer function which is not constant, right. Any filter usually will not have that, right. So when that is not so, then one kind of distortion is introduced. If the phase characteristics are not linear with respect to frequency, that leads to another kind of distortion, but both these kinds of distortion are linear distortions because they are arising from non-ideal characteristics of a linear filter which is modeling the channel. Okay, so there are two kinds of linear distortion. We are talking about linear distortion here. One is called the amplitude distortion, and this arises when this condition that the magnitude characteristic should be constant is not satisfied over the bandwidth of interest. Okay, if the magnitude characteristic of the channel are not constant equal to some value k, which denotes the attenuation, then we say that over the bandwidth of interest we say that the channel is introducing amplitude distortion, in the sense that the different frequency components present in the message waveform mt are being amplified or attenuated differently by the channel. An ideal channel would treat all frequency components in the same way, right, so that to keep their relative magnitudes the same at the receiver, right. But in this case certain frequency components may be attenuated less, certain other frequency components may be attenuated more, and this relative difference in treatment in terms of attenuation causes amplitude distortion, right. So this amplitude distortion does not tell us what kind of effect takes place on the output waveform, right. This is a characterization in the frequency domain, that in the frequency domain the channel does not treat all frequency components with the same attenuation characteristics. That's what it means. So don't think of any other connotation of amplitude distortion other than the one implied in the frequency domain. Okay, it doesn't tell us anything specific about what kind of waveform you might see, right. That should be very clear in your mind. For example, I'll give you typical attenuation characteristics that you might see in a telephone channel, for example. Usually these characteristics, magnitude characteristics, are plotted on a log scale. So I'm plotting here minus 20 log of HCF. What is it called? Decibels, right. So you're plotting the amplitude response in decibels. So the units are decibels. So a typical characteristic that you might see may look something like this, right. So you can see that there is a lot of variation, let's call this delta, in the amplitude or the amount of attenuation different frequency components may go through, right. I am plotting here only for positive frequencies, you can replicate for the negative frequency axis, okay. And so we are going to see characteristics like this which are not flat, right, which is what you would ideally like to see. As long as this delta is small, overall variation is small, you can ignore it, it does not matter, effectively it does not matter very much, right. What is the extent to which you can tolerate it? When this variation is within a dB or so, within 1 decibel or so, right, that is a rule of thumb for you to remember, right. So if the variation of the attenuation as a function of frequency, let us call that delta, is within a dB, within 1 decibel, the amplitude distortion is negligible and we can ignore it. But if it is more than a dB, it becomes significant and we have to take that into account. Okay, so that's what amplitude distortion is all about. As against this, we have the second kind of linear distortion, which we call by the name of phase distortion, or sometimes also called delay distortion. These two things typically mean the same thing. And as the name implies, this kind of distortion arises when your channel has phase transfer function which differs from the required ideal transfer function. What is the required ideal phase transfer function? A linear function of frequency passing through the origin, right. Odd function, it has to be, of course any real filter will have the phase function as an odd function, that is not an issue. So if it differs from that linear characteristics within the bandwidth of interest, we get the phase distortion. So if angle of HF is not equal to minus 2 pi T naught f, actually it won't matter if it is this plus minus, tell me something, plus minus how much? A multiple of pi, isn't it? If it is a multiple, if you go back to this equation that we were looking at, right, if I put a e to the power minus j m pi or e to the power plus j m pi, where m is an integer, this will be a constant value equal to either plus 1 or minus 1, which could be absorbed in the attenuation factor, right. So it does not really make any difference to the basic phase characteristics. So the required condition therefore really speaking is this plus minus m pi, right. So if this is so, there is no over the bandwidth of interest for f mod of f less than b. If this is not so, that is it, that causes phase distortion or delay distortion, right. If this is so, what is the amount of delay introduced at frequency f? T naught, right, and it's the same for all frequencies, right. If this is not so, basically what it implies is that different frequency components undergo different amounts of delay, and that's why when they combine together all these frequency components at the other end, at the output, the signal does not appear to be the same as it started with, right. So if this linear characteristics do not hold, it implies different delays for different frequency components. and that is why we also call it delay distortion, right? If every frequency component present in the message signal undergoes the same amount of delay, there is no delay distortion, no phase distortion. If different frequency components undergo different amounts of delay, there is a delay distortion. Now fortunately, in analog signal transmission like speech, right, particularly speech, delay distortion is not of much consequence. Reason is simple. Our ear is insensitive to delay distortion, right? This happens to be a property of our perception, hearing, right? But for speech, this is an exceptional situation. For pictures, for example, that's not true, right? Delay distortion matters because the eyes are not insensitive to the way I see a picture. It's not insensitive to phase information or delay information. And similarly for data, delay distortion can cause havoc. I'll repeat that. So this is just a practical observation that I'm giving here, that delay distortion not very important in speech transmission. When your message signal is basically a speech signal, what we are saying is, if the message signal happens to be a speech signal and if the channel introduces delay distortion, we are not too much worried about it. And the reason is because ears are insensitive to this kind of distortion. So to understand why that is so, of course you have to go into how the ear perceives the signal, right? We're not going to go into that right now, but that's just a matter of information for you. On the other hand, delay distortion becomes fatal if it is present when you are doing particularly data transmission, right? So data transmission is highly sensitive to delay distortion. Similarly for video, similarly for pictures, it is highly sensitive to delay distortion. Alright? So I have repeated what I was saying. In any kind of pulse transmission, right, which data transmission is a special case of that, delay distortion is going to be fatal, right? It causes a very severe kind of distortion, and if you don't compensate for it, if you don't take that into account in designing your receiver, you will not be able to do a good digital communication, right? So these are two kinds of distortion which fall within the domain of what I have mentioned as linear distortion. So whether we have amplitude distortion or phase distortion or both, we are talking about linear distortion. One important characteristics of linear distortion is that basically the existing frequency components, the message signal, will get treated differently by the channel, either in terms of their attenuation characteristics at different frequencies or in terms of delay characteristics at different frequencies, right? So that's linear distortion. One nice thing about linear distortion is that at least in theory, in concept it is very easy to compensate for it, isn't it? It's obvious. What should we do at the receiver? Put a filter which is a reciprocal of the channel transfer function. So in theory it is possible to remove linear distortion through a process called equalization, right? And that of course will have to be done at the receiver, right? So what we are saying is the message signal goes through a channel with a transfer function HCF. So what we must do at the receiver, have a filter with transfer function, let's say H sub EQF, where the product of these two together appear as a distortionless channel, right? So if this is an actual channel and this is your equalizer, what we like to have is that the equalizer should have this kind of transfer characteristic. Right? So that the product of these two appears like an ideal channel. Right? The product of these two is a net transfer function that the signal will see, the message will see, that should be equal to k times e to the power minus j 2 pi f t naught prime, let's say, some other value of propagation delay. Of course, this is required only for mod of f less than the bandwidth. So that the product, you can think of the product as some kind of an equivalent channel, right, satisfies the ideal characteristics. So in theory it is possible to take care of linear distortion perfectly. Of course, things are not as simple as they appear here. In theory is perfectly fine here, but in practice you can imagine there will be a lot of difficulties in actually implementing such an equalizer. Can you think of some difficulties? There are two major difficulties that will come up. One is, we are assuming that we know what channel transfer function is like. In reality, you will very rarely know anything about what the channel is doing. Right? You are transmitting a message, and what you see at the output of the channel is the received or distorted message. You know nothing about the channel. So unless you do something special, unless you make a special effort to learn about the channel characteristics, right, there is no question of trying to equalize for it. So that of course means more complication. To learn the channel characteristics so that you can implement an equalizer filter which is of this kind is a non-trivial effort, non-trivial job. The second problem that may arise, even if you knew the channel transfer function is, suppose you knew the channel transfer function, is due to the fact that we have ignored another very important component which is present in the channel, noise. Right? Suppose the channel HCF has a null over in the range of some frequency components within the within the message bandwidth of interest. Over a few frequencies or in the neighborhood of some frequencies, the channel exhibits very deep attenuation, very large attenuation. Suppose it happens. It can happen, right? Then what will be the required equalizer characteristics at those frequencies? Very large amplification of those frequencies. And if you implement that, you can do that. What you are also going to do is amplify the corresponding noise components there, right? So you may undo the effect of distortion, but you may be introducing or enhancing the effect of noise, right, which may not be desirable. So in theory this is all fine, but in practice one has to work out a solution which takes care of these concerns. Okay, we will not go into further details at this moment. This is a subject which is properly dealt with in a course in digital communication. Because
is the transfer function of the channel always constant, as it doesn't vary in time?
We are assuming in this, that's a good question. The question is, the channel can we assume the channel to be having a constant transfer function for all time, or in other words, is it proper to think of the channel as a linear time invariant system? The question can be rephrased like this, right? Because I talked about linearity, but I didn't talk about time invariance. It's a good question. The answer to this question is yes in some channels, no in some other channels. The discussion that we are doing right now is for those channels where it can be modeled as an LTI filter, right? There can be channels in which it cannot be modeled as, it can be modeled as a linear filter, but not necessarily time invariant, right? For example, a wireless channel in which there are lots of reflections from various objects in the propagation path, and these objects keep moving or you keep moving, right? Obviously it's a linear characteristic, but it's not time invariant. It's linear time varying characteristics. Then of course our discussion has to this equalization business becomes even more difficult, because not only you don't know, it keeps varying with time, right? So how to handle it both theoretically as well as practically becomes a very major issue. But these are issues which are beyond the scope of this course. At the moment we will not discuss those, but at least you know that it can be done and what the concerns are. Okay, any other questions? So that is as far as our discussion on linear distortion is concerned. Now I have been emphasizing this concept, I mean this adjective linear, right? And that's because we can also have a kind of nonlinear distortion. And as the name obviously implies, this kind of distortion would arise in a communication system in which in some part of the communication system or the other there is some kind of non-linearity. Okay? Can you think of any kind of non-linearities which can crop up in a communication system? Which are the components which can give rise to some non-linearity? Amplifiers, very correctly said. Particularly power amplifiers, right? Not the voltage and current amplifiers, but power amplifiers. You've done some course on power amplification, some discussion on power amplification, class B, class C amplifiers, right? And these are dependent on, let's take one of these power amplifiers. Whatever knowledge you have is sufficient for our discussion. Under what conditions do they work most efficiently or very well? They are supposed to work very well. They work very well if your amplitude of the input signal remains constant, right? If the amplitude fluctuates a lot, first of all, they don't work very efficiently. But that's not of concern here. Efficiency is not what we are considering here. We are more concerned about the fact that if the amplifier gives different amounts of amplification depending on the amplitude of the input signal, it treats the low amplitude signals in some way and the high amplitude signals in some other way, then we have a kind of nonlinearity. So if you were to typically, so let me first mention what nonlinear distortion is. So this arises due to nonlinear, now this is, please note what I am writing, nonlinear transfer, not transfer function, because nonlinear systems I cannot study in terms of transfer functions. I cannot study in the sense, I mean we are not talking about frequency domain here. I am saying due to nonlinear transfer characteristics. What are transfer characteristics of a device like an amplifier? How do we show a transfer characteristics? These are the devices which can exhibit nonlinearity. Amplifiers, mixers, etc. We still have to talk about mixers, we will talk about them later, but let's talk about amplifiers. So when I say transfer characteristics of an amplifier, and if you were to plot it, what is the plot that I make? I simply plot output versus input. Output Y against input X, and we are here referring to the amplitude of the output versus the amplitude of the input, right? So in fact ignore the time variable here, that is of no consequence, right? What will be the output input characteristics or transfer characteristics of an ideal amplifier? Straight line, isn't it? Input is small, output should be small. Correspondingly, if the input is large, the corresponding output should be large. Simple. Nothing beyond that. So it's a constant times the input. Y of t should be equal to, ideally y of t should be equal to some a times xt, where a is the amplification factor, right? That's the transfer characteristics. Now practical power amplifiers will exhibit a kind of nonlinearity which is very commonly encountered, called the saturation nonlinearity, right? You know the effect. It basically arises because you have some finite values of the power supplies, and because of this, as your input signal becomes larger and larger in amplitude, instead of being linear like this, you get into this nonlinear or saturation mode like this. It doesn't remain linear for all values of the input amplitudes. So as long as your input signal is within the linear range, you are fine. But if your input signal goes beyond the linear range, right, then the output is no longer proportional to the input, right? Y of t is no longer A times xt, right, and that is a nonlinearity. Now basically if you were to model this nonlinearity, you can see that you cannot model it as a straight line kind of relationship, a linear kind of relationship of this kind. You have to introduce, can you suggest some model for this curve that you have here, some suitable parametric model? For example, we can possibly model it as a polynomial of some kind. We can find out suitable coefficients of a polynomial such that the resulting curve would look like these characteristics, and that's a usual thing that is done to model nonlinear components, nonlinear devices, right? Use polynomial models. So a typical model, for example, for such nonlinear things would be that y of t is a1 times x of t, which would have been the ideal thing, right? But you also have additional terms like a2 times x square t plus a3 times x cube t, and so on and so forth. And theoretically it is possible to find a set of coefficients a1, a2, a3, etc. With a polynomial of some degree, suitable degree, such that this resulting characteristics resemble the actual curve that we have plotted, right? Y versus x curve that we have plotted. Now suppose that is the case. Suppose let's take very simple, suppose we take a very simple nonlinearity of the kind a1 x t plus a2 x square t. One thing is clear, that the output is not a replica of xt, right, and therefore there is a distortion, right, because we would like the output to be simply proportional to xt, but we have additional components like x square, x cube, and so on and so forth, right. So therefore there is a kind of distortion here. Now how does this distortion differ from the linear distortion that we have discussed? In one very, very important and very significant way. If you remember, I had made a comment about when we talked about linear distortion, that linear distortion which arises due to non-ideal characteristics of the channel in terms of its transfer function can only do something good or something bad relatively to different frequency components that exist in the message signal, right. So but it cannot create additional frequency components, isn't it? A linear filter essentially affects whatever frequency components are present in the message signal. It will amplify them differently, attenuate them differently, or delay them differently. That's all it can do. That's the linear distortion. Nonlinear distortion, on the other hand, has the potential to generate frequency components in the output message signal which were not even present in the input signal, right? And that's the very important way in which nonlinear distortion differs from the linear distortion. Let me give an example. Suppose the input signal is a pure sine wave, just for the sake of appreciating this point, right? Pure sine wave of frequency, let's say f1, right? Now what are the components present here? This will be a1 cosine 2 pi f1t plus a2 cosine 2 pi f2t whole square, cosine square, right? So cosine square you can write as 1 plus cosine 4 pi f1t, right. So now what are the components present in y of t? We have f1 and 2f1. 2f1 was not present. The input was containing only f1, right. So the input signal contains, let's say, a frequency component f1, output contains f1 as well as 2f1. This is a very simple situation. Suppose now the input signal contains two components, f1 and f2. What will you have now? You will obviously have f2, f1 2f1, and you will also have f2 2f2. In addition, you will have f1 plus minus f2. Right? You can see that. It's a matter of just writing down the trigonometry and seeing that you will get terms which is cosine of 2 pi into f1 plus f2 times t and 2 pi f1 minus f2 times t. So these additional frequency components that are getting generated is the real problem in nonlinear distortion, right? And that we call these components intermodulation components. And this nonlinear distortion is for this reason also called harmonic distortion or intermodulation distortion, because different frequency components modulate each other to produce additional frequency components, right? So therefore another name for nonlinear distortion is, another set of names in fact, harmonic distortion, because additional frequency components are being present, or intermodulation distortion. And that's, is that good or is that bad? It's very bad, right? Why is it bad? Can you appreciate? Can you suggest? Power is an issue, but it's a less of an issue. It is creating components outside. Suppose you have a signal of bandwidth B. Your distorted signal will have components much beyond B, right? And obviously you are going to speak into somebody else's band. Suppose you are allotted a certain frequency band to work with, you are transmitting outside that band. Your received signal contains components outside the band. If your receiver was now trying to look for a signal in that frequency band, it will not only see that, but will also see some components from this, and this will cause a kind of crosstalk, right? So this will call what is called radio. It's also called co-channel interference. Also, or sometimes also simply called crosstalk. Right? Yes, please.
So does harmonic affect the power of the fundamental frequency that we are using?
Yes, because you can see that these characteristics, that will now depend on the value of these coefficients, right? So how the power gets divided into different frequency components will depend on the values of these coefficients in the model of the nonlinearity. Right? Any other questions?
So these new frequencies which we got, so they can create problem only if they are in the order of the original frequency which we had. Suppose I took F1 and left off such an order, and the frequencies are too much high compared to this one.
Yeah.
Then it won't be causing any problem.
What you are saying is if F1 and F2, F1 plus F2
It's comparable to F1 or F2 only, then I will be having it.
No, the point is you are not only going to see, you are definitely going to create a distortion for yourself, right? That is obviously happening. So within the frequency band you have some frequency components and you are generating additional frequency components. These additional frequency components may lie within the bandwidth of interest or they may lie outside the bandwidth of interest. They will typically have both kind of situations, right? F1 minus F2 will typically lie within and F1 plus F2 will lie outside, right? So both kinds of things are bad. F1 minus F2 creates distortion for us, F1 plus F2 creates distortion for somebody else, crosstalk for somebody else, and so on and so forth. Right? Okay, we'll stop here unless there is some other question. Thank you very much.